All right, I will, well, I guess I'm technically not supposed to start yet. I'll wait a second. Oh, who cares? Let me start. Everybody here is here, so I'll begin with a word of prayer. Heavenly Father, we thank you for this day. Again, I thank you for this class and this time we have to meet and study your creation. Just pray that you would be glorified in what we do, Lord. In your name I pray, Lord Jesus. Amen. All right, so I have introduced the concept of quotient space last time, and I almost proved something about it, I guess. We proved some things about the quotient, right? We proved that two cosets are equal if and only if the difference of their representatives is in the subspace forming the quotient, right? We proved that. And so one of the main results we proved last time, right, was that for W, a subspace of V, we have X plus W is equal to Y plus W, if and only if X minus Y is an element of W itself, right? And we defined the quotient W to be the quotient vector space, which is X plus W, such that X is in V. And if we use the notation, the coset represented by X is brackets X like this. So this is X plus W. Then, for instance, 0 would just be W itself, right? So it's effectively the subspace behaves as the 0 for the quotient space, right? So the whole infinity of points, which perhaps is in W, becomes, come on, no. There, better. So the subspace behaves as 0, and in this notation, to add to points in the quotient space, we simply add the representatives, right? And to scalar multiply, we simply scalar multiply the representative. And I mentioned that you can prove that these definitions of vector addition and scalar multiplication does in fact make the quotient vector space of V by W a vector space. But I suppose it would be good for us to maybe sort through one of those axioms. So let's try this one. Let's check an axiom. Hopefully I won't check the one that I asked you to do in the homework. Actually, did I ask you to do any in the homework? I don't remember. Maybe I didn't. Bah. Oh well. How about, so which you want to do the one about the addition of scalars? Let's try that one. So suppose you've got like C1 plus C2 times X. What's that? By definition, this is C1 plus C2 times X, like that, right? So this is definition of scalar multiplication in the quotient space. All right. And then what's next? Well, next, we know that that's equal to C1x plus C2x, right? By the axioms of V, right? So by the corresponding axiom of vector spaces, we have this distributive property for scalars, right? But then what? Well, then by the definition of vector addition in the quotient, this is C1x plus C2x, right? That's the definition of addition in the quotient vector space, right? And then what do I do? Next step, finishing blow here, I go back, I use the definition of scalar multiplication in the quotient vector space 2 times, right? Pull the C1 out here, pull the C2 out there, and so again, definition of scalar multiplication in the quotient. And I think at this point we have demonstrated that axiom. I've forgotten the number. Do you remember? Okay, just checking. So, might be 8. I know it's not 1. I know it's not. The first 4 are about like the group properties of the vector space. So it's one of the last. 8's probably it. But there it is. And the proof of the other axioms is very similar. Like if you wanted to prove the associativity of the scalar multiplication, essentially, it rests on the definition of the quotient space and then the fact that the corresponding axiom can be applied inside the brackets, and then you undo it. All right? Great. So it is, in fact, a vector space. It's a new vector space, though. The points in the new vector space are themselves different objects than we started with, right? So the quotient vector space is not a subspace of V. And it's not W either. It's something genuinely new, right? But it does reveal all kinds of stuff about V and W. And one of the reasons for that is the following theorem. For V with W, a subspace of V, finite dimensional, over F, the dimension of the quotient space of V by W is simply equal to the dimension of V minus the dimension of W. All right? Well, let's prove this. So here's the proof. We should do what? We should begin with, let's say, beta sub W equals to W1 WK basis for W, right? Why can we do that? Well, if it's a subspace, we know that every vector space has a basis, so there it is, right? And then we also know that we can extend that basis to a basis for V, right? And we'll say, V1 dot 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 Vn minus k, and then W1 WK, a basis for V, right? So I'm letting n minus k be the number of vectors I need to adjoin, possibly. So here I'm assuming, I assume the dimension of V is what? N, right. Because for this counting up here to work out, we've got n minus k things plus k things. I should get n things, right? All right. So now you guys tell me, what do you think the basis for the quotient space should be? What do you think we should argue is a basis for the quotient space here? Yeah.
For instance, V1 plus W, V2 plus W, V3 plus W.
Okay. So you're claiming that I'll call it gamma for lack of imagination. Gamma equal to V sub I plus W, such that I equals 1, 2, dot 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 n minus k is basis for V by W. I think you're right. Now, why do we know that we can't possibly include, like W1 through WK, any of those as representatives? Like, why can't those be part of this possibly? This isn't really part of the proof, it's just, a comment. So note, if we look at w sub, let's say j, plus w, right, what's that equal to? Well, it's equal to w since wj is an element of w by construction, right? Which means w sub j is just a representative for the zero vector. Everything in the basis for w represents the zero vector in the quotient space. They're all 0. Can we put 0 in a basis? No can do'sville, right? No, 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 no. Don't do it. Wouldn't be prudent. So now the claim is that what I wrote in red there is a basis. So okay, let's work it out. Let x plus w be an element of the quotient space, right? Then of course we can write x as what? A sum I equals 1 to n minus k of x sub I v sub I plus a sum, let's say j equals 1 to k of, I guess I'll say y sub j w sub j. So I'm writing x as a linear combination of things in the basis beta, right? This has to be possible because beta is a basis, right? And so that's what an arbitrary x expands as. So then what's the deal though? If we look at x plus w. So we've got ourselves, the sum I equals 1 to n minus k of x sub I. And if you don't mind, I'm going to make a step right here. I'm going to use the definition of the quotient space to rewrite this as like vi plus w plus the sum. So what I'm doing here is I'm using the vector addition. Well, really, I guess we proved by induction at some point we could extend from 2 things to k things, right? But I'm pulling the constants out, as is my right, and I am, leaving it just in terms of the cosets. Hopefully that's helpful. So that's just by definition of the scalar multiplication and vector addition of the quotient space, right? I pulled the constants out just to emphasize what's going on. Now, of course, as we've just talked about, this is equal to the following, and you guys tell me why. Exactly. Because this is nothing more than the zero vector. And if we add the zero vector together a bunch of times, it's just the zero vector. That's right. So then what? Oh, well then this is an element of the span of gamma, right? Do you guys see that? So apparently, Sam's intuition's right. It's at least a generating set. Now can we prove it's linearly independent? What do we need to do? Let's check the linear independence of gamma. How should we do that? Is z equal to 0? That's right. So we've got the sum I equals 1 to n minus k of, we could use x sub I here. If you want, I can put, I'll do c sub I. We traditionally do c sub I here, so I'll put some c sub i's. That'll make you feel better. Plus w is equal to 0, right? But what is that 0? To be clear, we're talking about w itself, right? And to be more manifest, what we're really saying is that the sum of Ci vi I equals 1 to n minus k, that vector plus w is equal to w, right? So again, by the definition of the quotient vector space, addition and scalar multiplication, I'm rewriting it instead of a sum of cosets as a coset of a sum. Instead of a sum of cosets, a coset of a single sum. And then I know that it must be then that the sum I equals 1 to n minus k of Ci vi has to be an element of w by the theorems we proved last class. Right? The only way something plus the subspace is equal to the subspace again is if that something is an element of the subspace. But what are the v's? V's are the extension of a basis for w. If this was anything but 0, this would imply a linear dependence of the basis beta, which is of course absurd. Therefore, I'll put it this way, since beta is a basis, we have that the sum I equals 1 to n minus k of Ci vi has to be equal to 0. But then again, since beta is a basis, what do the coefficients have to be? C1, Cn minus k all have to be equal to 0 as, by linear independence of beta. And then the rest is just counting, right? Because the dimension of the quotient is the number of vectors in the basis for the quotient space, which is manifestly n minus k, whereas the dimension of v is n, the dimension of w is k, and n minus k is n minus k. So n minus k equals n minus k. We're done. So there you go. I hope this makes sense. All right. So example 1, if we had v was like, I don't know, maybe it's the span of 1, 1, 0, 0, and 0, 0, 1, 1, that's not v. I want that to be w, right? And of course, that's a subspace of R4, right? Then I'd like to say v mod w is the span of two things, right? Can you tell me how to fill in those blanks? I'll tell you what, I'll get us started. There is no way I can get this as a linear combination of these two. I don't think. Because I'd have to add them together to get 1, 1, but when I do that, I get the 1s on the outside. So let me just put A, B, C, D here, and I want to show you some. I haven't talked about this at all this semester, right? And in some sense, this is putting the cart before the horse, but I think it's worth it. It's worth it. What condition on A, B, C, D do you need in order for this to be true? Like, we need for the 4 vectors that are pictured to be a basis for R4. What's the easiest way to check that these 4 vectors are a basis for R4? I'm just following the proof over here, right? Which was we pick a basis for the subspace, which was given, and then we simply extend it to a basis for the whole space. Those form the representatives of the quotient. So here's the trick that's, I think, the fastest way, is just calculate the determinant. 1, 1, 0, 0, 0, 0, 1, 1, 0, 1, 1, 0, A, B, C, D. Or of course you could make it, you could transpose that, right? And set that not equal to 0. Any solution to that will do. Right? So if you're looking to construct a basis for Rn, and if you already know n minus 1 vectors, a nice way to find the next one is to use the determinant. Admittedly, logically speaking, in this course, in its self-containedness, we've not defined determinant yet, and we'll be doing that in about a week or two. But in the meantime, if you want to use determinants to help you with some homework problems, feel free. This might be useful because you've got some problems where you're trying to find a vector that's outside of the span, and determinant can be very useful for finding something outside of the span. Just saying. I digress. Let us get back to the beaten path here. So I wrote a whatchamacallit, what's it called? An appendix to the notes, right? And, oh man. And I wrote an appendix on like functions and images of sets under functions and things. And this is the point in the class where I should just talk a little bit more about that, just for the sake of generality. See, because the next topic here is the first isomorphism theorem. And the first isomorphism theorem is something deeper than just linear algebra. I mean, there is something deeper here, and it concerns the general problem of if you have a function, how can you elevate it to something that's invertible? You ever thought about this? So like, here's the general discussion. Suppose you got a function, and it goes from a set A to a set B, right? And you'd like to make that a bijection. What should you do? What does it take for it to be a bijection? It needs to be what? 1 to 1 and onto, right? So if you want to make it onto, what do? It's kind of dumb. What's that? Restrict B, right? Yeah. So we don't. I don't have a name for that, but you're right. We replace the codomain with the range, basically, right? So you say, okay, well, I'm going to instead look at f from A to f of A, right? So hooray! Now it's automatically onto. Well, that was easy, right? How do we make it 1 to 1? What does that take? Well, let's think about that. So for 1 to 1, we need f of x equals to f of y, right? To imply what? Imply x equals to y, right? And this is, if x and y are in A, then if we have this, then the mapping is 1 to 1, right? But we're not guaranteed that, are we? We're not, right? In fact, if we look at the inverse image of, let's say, little b, so let b be an element of f of A, right? Something in the range. Then what's the inverse image of b? What is that defined to be? So what we're talking about is x in A, right? Such that what? Where does it map to?
F of x equals b.
F of x equals to b, right? But at the moment, f of x is an element of the singleton containing b, but you're right. You saw through me. That's really just x in A such that f of x is equal to b, logically equivalent to the statement above. Great. So this is called a fiber of f. The inverse image of a singleton. A singleton is a set containing one element. So another way to look at this, right, is that for a function to be 1 to 1, what do we need to be able to say about all the fibers?
They all only have a single output.
Right. So this means that we need f inverse of B is a singleton, right? For each B in f of A. Now, if we didn't do this game at the start, if we hadn't started by throwing away everything in the codomain we don't map to, we'd have to replace this discussion with saying every non-empty fiber is a singleton. Because generally speaking, the picture is something like here's a picture you can draw to kind of illustrate what's going on. So here's B, here's A, here's F, right? And there's part of B, which is, the image, this part up here, right? But down here is the part outside, right? And if I was to take a point in here, right, it's like a point which is not an element of the image of F, right? And then I take the inverse image of such a point, what do I get? I get the empty set, right? There's no point in the domain which maps to that. So the inverse image of a point outside the range is just empty. It's an empty fiber. But as long as we're looking at the fibers over here, like B, well, you're getting something over here which is like F inverse of B. Let me call that B1. And if I had another point over here, say B2, I could look at, F inverse of B2, right? And you can prove, in fact, that this defines an equivalence relation on the domain called the fiber equivalence. 2 points are equivalent in the domain if and only if they're in the same fiber over the map. I can make that more precise. X is equivalent to Y if and only if f of x equals to f of y. It's kind of dumb, but there it is. In other words, they both map to the same output. They're equivalent. So the question then is, how do you take f then and make it into a bijection? Well, one simple way is you can take a cross section. Basically, a cross section is something that I could call S, like a cross section. And the deal with S is S intersects each fiber at most once. How do you construct a cross section? Axiom of choice. You just pick an element from each fiber one at a time using the axiom of choice. You can do this. And if you did do this, if you had F restricted to the cross section, a mapping from the cross section to this, that would be a bijection. Now, pragmatically speaking, I can let me give you a nonlinear algebra example of this. Is usually my go-to example. If I'm, like F, a mapping from, say, R2 to R, and we say f of xy equals to x squared plus y squared, this is pretty easy to understand. Anybody want an umbrella? Nobody? Oh, you? Okay, here. It's yours now. So this thing, right? First of all, what should I do to make it onto? We could remedy, let's, what am I on example 2? All right, so example 2. So to fix this, to make it onto, I just erase this, right? And say what? Instead, we do what? 0 to infinity, right? Because x squared plus y squared is non-negative. Great. What do the fibers of this map look like? What is f inverse? And let me write it suggestively. Any non-negative number can be written as r squared, yeah? So what's the inverse image of r squared? circles and the origin. And so you got the point at the middle, beep boop, and then concentric circles. These partition the plane. These partition the plane, you see? Every point in the plane is in one and only one fiber, which is a circle. And this mapping is not a bijection, it's not one-to-one, right? Because every one of those, the whole circle, the whole infinity of points on the circle, all maps to r squared. So how can you make this into a bijection? Well, what you could do, if you wanted to, is you just, instead of looking the whole domain, you just, how do you find a cross-section here? It's kind of obvious geometrically. You do what?
Just one axis?
Just one axis, right? Just pick an axis, pick a ray, whatever. Like this could be your S. Or you could pick the real axis if you like. If you pick the real axis, then the inverse image, like the inverse map, actually would just be, you know, well, you could write down the formula. So this is what you could do to make a mapping invertible if you were just going to merely play with set theory and just, instead of taking the whole domain, just, you know, take part of it, all right? But the first isomorphism theorem is more clever than this. But it's really kind of after the same idea, which is how do you take a linear map and make it into an isomorphism? All right, how do you do that? Okay, so in order to properly understand that, we should understand what is the fiber of a linear map. Let's calculate that. What's the inverse image of a point for a linear transformation? You guys calculate it while I'm erasing here. So let T be a linear map from vector space V to vector space, oh, let's call it W. You tell me. What's
Just every element.
Write it out. Write it out.
Write it out.
Write it out. Yeah, so we have T from V to W. Excuse me. So my question is, for W in T of V, right? Calculate T inverse of W. What would that look like? Can you guys work out what that looks like? What does it mean for something to be in the range? For W to be in TV, W has to be equal to what?
W equals T of V for some V and V.
Sure.
Well,
Yeah, I want to use
bad choice of
maybe X. Yeah. I mean, W is already a bad choice on my part. I probably should put Y here. Would that make you feel better? Here you go. Y. I already feel better. So this is equal to what? This is equal to X in V, such that, you know, T of X is equal to Y, right? Can I just go straight to that? Is that okay? So what does that mean?
can't really think of a way to simplify it.
There's only one X that's on top.
Let's try to, so Y is fixed here, right? let's try to relate it to the kernel of t. Maybe we can make progress if we do that. So is this, here's my question, is question mark, is this equal to, you know, like x naught plus the kernel of t? Is it a coset of the kernel? What would it take for this to be
Well, if y is 0, that is the kernel.
okay? If y is equal to 0, it is the kernel.
So is that just y plus the kernel of t?
How would we prove that?
It is x naught plus I log t. And it has a degree of freedom. Which means it's not single.
Well, yeah, it depends on how big the kernel of t is. That's right. So, well, that's a good point. If, well, it kind of assumes the point. We should be able to show this. I'm hitting a mental roadblock at the moment. But you could prove that the fiber of a linear map is just a coset of the kernel. This we could prove. Maybe I should make that a homework problem since we're stuck on it right now. What do you think? No? No? Well, I just don't know the answer right now because I was up until 4 writing a solution for my differential equations quiz. But because before, well, anyway, it's not interesting. But this will hit me later. This is not hard to show. It really isn't. All right. Well, so we can write x as equal to, let's say, I don't want to, let me just put, well, okay, fine. I'll say x, xk plus x not k. This is a horrible notation, but where xk is an element of the kernel of t. Why can I do that? Because kernel of t is a subspace, right? So I can find a basis for the subspace, and I can expand any vector as a linear combination of that basis plus whatever's not in the basis, right? Either x is, okay, so anyway, my point is I can expand x into the part which is in the kernel and the part which is not in the kernel. I think that's not too much of a jump for you guys. And then what happens when I look at t of xk plus x naught k? That's t of xk, right? Plus t of x naught k, right? By linearity of t. But if that's the kernel part, that's 0, and we just have t of x naught k, right? But this is still my, I'm assuming that I've got t of x, right, equal to this. And this is all equal to y in this discussion, right? So look at what you have. You have t of x equals to y, but you've also got this equals to y, right? So what does that tell you about t of x? Yeah, probably not 1-to-1. Good point. Good point. Probably not 1-to-1. Tx not k minus x is equal to what? Apparently it's equal to 0, right? Which then means that Tx not, the not kernel part plus kernel of t, right, is equal to x plus the kernel of t. Oh, anyway, I'm sorry, I can't see my way through it. I'll have to make it a homework problem. We can prove, in fact, that the inverse image under a linear map is literally just a coset of the kernel. All right, it can be shown. I'm struggling at the moment. I really should have made it a homework problem anyway. Yeah, right, yeah. Okay, so then what? You're right, if the kernel is 0, then this just becomes, you know, a singleton, right? Because the coset of a singleton is a singleton. But otherwise, it's not, right? So linear maps are injective only if the kernel is 0, because that's the case where the fibers are singletons. So then, moving along here, let's talk about the first isomorphism theorem, which I should have started talking to you guys about 10 minutes ago, but apparently I got stuck. So come on, computer. Oh, we still got 8 minutes. We're good. So here's the deal. If we have a linear transformation, so here's basically the theorem. If we have a linear, although I need to define the quotient map first, but I'm just going to get through it here. So T, a linear transformation from V to W. All right. We define the projection, well, the quotient map by X to be equal to the coset of the kernel. All right. Then we can define T bar as a mapping on V mod the kernel of T to W by T bar of X plus the kernel of T is simply equal to T of X. We can prove that T bar, let me call it T prime. If we do the thing that Gideon suggested at the start, we swap out the codomain for the range, right? If we do T prime is a mapping from V mod the kernel of T to, well, T of V is an isomorphism. In other words, you can prove that V mod its kernel, mod the kernel of T, is isomorphic to the image. This is the first isomorphism theorem. And I don't want to hurry the proof of it. I'm going to take next class, and I'm going to take about 10 minutes and prove this carefully, all right? I don't want to hurry this. What I do want to show you with the time we have remaining is an application of it. Let's see what this does for us, because it's going to do something really, really amazing. So suppose you look at the mapping, say, n by n matrices to, oh, I don't know, n by n matrices. And we're going to define the mapping like this. T of A is equal to 1/2 A plus A transpose. All right? This is a linear transformation. What's its kernel? So we're talking about A in Rn by n such that what? In other words, we're looking at A n by n matrices such that A transpose is minus A, right? These are the so-called skew symmetric, right? Skew symmetric matrices form the kernel. But what's the image of this map? If we take T of A and we transpose that thing, what happens there? Yeah, exactly. We get exactly what we started with, which means what? It's in the so-called symmetric, my notation at the moment, the symmetric n by n matrices, right? It's a symmetric n by n matrix. In fact, we can argue that the image of this map is the set of symmetric n by n matrices. Pick any symmetric n by n matrix, the proof that it's onto, right? let B be an element of Sn. Do you see it's onto? This proves it's into the symmetric matrices. Let's prove it's onto the symmetric matrices. If B is in Sn, then T of B is what? 1/2 B plus B transpose, right? But B is symmetric, which is to say that this is 1/2 B plus B, also known as B. So therefore, T onto Sn. All right? So let's apply the first isomorphism theorem. What does it tell us? It tells us that if we take Rn by n and we quotient by the set of, the kernel of T, which is the anti-symmetric, which I don't apparently have a notation for, n by n matrices, right? That is isomorphic to what?
Symmetric.
The symmetric n by n matrices. How does the dimension of this all work out? So the dimension of Rn by n minus the dimension of the antisymmetric n by n matrices, which I'm going to call A sub n for the sake of not writing it again, is equal to the dimension of the symmetric n by n matrices. But we've seen all this play out on the test and the homework, right? Because the dimension, this is n squared, and this is n squared minus n divided by 2, and this is n squared plus n over 2. And if you take this minus that, you get that. Not an accident. The quotient theorem, rather the first isomorphism theorem, can help us weave these ideas together. So there's 3 problems in your homework where I say, look at this map, apply the first isomorphism theorem. So what you need to do there is figure out what the kernel is and think about what the quotient by the kernel is and what the image is and what isomorphism the first isomorphism theorem tells you. So, but to summarize, when we take the quotient space, what we're doing is we're selecting one, effectively, instead of choosing one element for the cross-section, like I was talking about set theoretically, we're allowing all possible representatives and we just view them as equivalent. But because we view the equivalence across the kernel as being, all those points being the same, representative of the same point, it's kind of logically the same thing that we're doing with the cross-section idea. It's just rather than just picking one point of an infinity, we're saying all the infinite points that are in the coset of the kernel, they're all the same point. And we're just squashing them all together in the quotient space. So, sorry about getting hung up on your homework problem, but yeah. I'll try to find a way to make it more understandable as a homework problem.